Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Find the punishment number of an integer, Leetcode 2698. If you are new to the channel, consider subscribing. I try to make daily videos on the problems related to data structures and algorithm, including detailed explanations, optimized solutions, and step-by-step walkthroughs to help you improve your coding skills. Now to the problem. In this problem, we are given a positive integer n and we have to return the punishment number of n. The punishment number of n is defined as the sum of square of all the integers I such that I is less than equal to n and greater than equal to 1. For example, here n is equal to 10, so I will be in the range 1 to 10, and the decimal representation of I into I can be partitioned into contiguous substrings such that sum of integer values of these substrings is equal to I. So for these integers as I, we have to calculate I into I or I square, which will be 1, 4, 9, 81, 100. Now we have to take each of these I squares and try to partition it and see if the sum of partitions add up to I itself. For example, let's take I square equal to 1, and only way we can partition 1 is that we get 1 itself. So we sum up this partition and we will get the result as 1, which matches I equal to 1. Now let's take a better example where I square is equal to 81 and I is equal to 9. So one way to partition 81 will be like this, where the sum of the partition will be equal to 81, which is not equal to 9. But another way can be that we create a partition between 8 and 1. Then the sum of integer values of these partitions will be equal to 8 plus 1, that is 9, which is equal to I. Now let's take I equal to 10 with I square is equal to 100. And again 100 can be partitioned like this, and sum of these partitions will be equal to 10 plus 0, which is equal to 10, that is I. So this is also a valid I for punishment. So all the I's we saw so far were valid I's for punishment. But now let's take one more example where I is invalid for punishment. For example, let's take I equal to 7 and I square is equal to 49. And no matter how we partition like 49 or 4 plus 9, that is 13, we will not get it equal to 7. So we will not consider these i's, right? And now in the end, the punishment of the number is sum of squares of i's. So for example, 1 square will be equal to 1, 9 square will be equal to 81, and 10 square will be equal to 100. So we have to sum them up, and in this case we will get sum as 182, and this will be our answer. To calculate the punishment number of n, we need to check for every number I from 1 to n whether I into I can be partitioned into substrings that sum up to I. If it can, we add I square to the punishment number. So then our approach can be that we start iteration from I equal to 1 and move up all the way up till n. And then for each I, we compute I square and see if I square can be partitioned. If it can be, then we add I square to our punishment number. And once we are done with all the numbers in the range, we will return this punishment number. And now let's see how we can check if the square of this number I can be partitioned or not. Now because it involves partitioning, we must convert this squared number to string to make the partitioning easy. Because otherwise, if we treat them as number, we would have to manually divide these numbers into parts by dividing it by 10 or 100 and so on. So that's why whenever we have to partition, it is preferable to use string. And now when we are doing the partition, we have to explore all possible partitions that we can do. For example, if I square is equal to 100, we can partition like this, which will give us 1 plus 0 plus 0, that is 1. Or we can do the partition like this, which will give us 100. Or if we do the partition like this will give us 10. So we have to explore all the possible ways this string can be partitioned. And this is where backtracking is a natural fit, because then we can systematically try out all possible substring partitions and ensure we explore only the necessary path. And in case the path doesn't lead to a solution, it backtracks or abandons that path and start afresh for the next potential option. Now let's see how we can use backtracking to check if the string can be partitioned or not, such that the sum of the partitions is equal to I. Let's take n equal to 37, for which one of the values for I will be equal to 36, and 36 square will be equal to 1296, which we can try to partition like this. First we try to create the partition between 1 and 2. So we will get the number 1, and we have to still partition the remaining string 296. We'll do that shortly. Then we can partition a string between 2 and 9, which will give us number 12, and remaining substring 96 have to be partitioned. Or we can partition between 9 and 6, which will give us number 129, and remaining substring will be 6. Or we can partition after 6, and this will give us 1296. And here we can see that 1296 is already in the terminal state because we have covered entire string, and the sum of the partition is equal to 1296, which is not equal to I equal to 36. So this is not a valid partition. Now for the remaining tree, let's try to recursively partition the remaining part of the string. Similarly, after 1, we have the string 296, which we have to partition. So we can partition it like 2, 29 or 296. So now if you see, this is also a terminal state because we have traversed through all the characters in the string, and the sum of this path will be 1 plus 296, which is equal to 297, which is not equal to I equal to 36. So this is also not a valid partition. Similarly, after 12, we can have 9 or 96. And again, this is a terminal state. And here we have sum as 108, which is not equal to I equal to 36. So this is also not a valid terminal state. And after 129, we have only 6, which sums up to 135, again not equal to 36. Hence, not a valid terminal state. So this is how we will continue doing the partition. And eventually, we will come to this path where we have 129, and then we will have 6. And this is again the terminal state because we have covered all the characters. And when we sum up all the partitions, we will get sum as 1 plus 29 plus 6, that is 36, which is equal to I equal to 36. Hence the partitions are valid, and we will return true from this path. Here is a more elegant depiction of state space tree, which if you are interested is also available via the link in the description below. And now coming to the backtracking algorithm, we will need our input string, which is I square string, the target sum, which is I itself, and the index IDX, where we are making the partition, and the current sum to keep track of the sum of the partitions we have done so far. And in the terminal state, we will check if we have explored all the partitions, that is, the partition index is equal to length of the string. In that case, we will check if the current sum is equal to target. If it is, then we will return true, otherwise we will return false. And then we will try to do the partitions and check if in any path we can get a valid partition, then we will return true, otherwise we will return false. And we will cover more of it in the code walkthrough. Also, one slight optimization that we can do is whenever the sum of the partitions exceeds the target, we can stop the recursion and backtrack early. Because if we create more partitions here on, the sum of these numbers will go higher and higher, which will never meet the target. For example, when our current sum here becomes 129, there is no point in adding 6 afterwards because the number will become even higher, which is 135. So from such situations, we can return back earlier. This approach is called pruning, where we cut off the branches in the search space or in the recursion tree that cannot lead to a valid solution. However, it won't change the time complexity, but it will make the solution more efficient. And now the time complexity of this approach is O of n into 2 to the power of d, where n is the given input and d is the number of digits in the numbers on average. For a single number I, we are calculating I square in O of d time, where d is the number of digits in the square of I, and then we check for valid partitions that will take O of 2 to the power of d, because there are 2 to the power of d possible ways to split the d digits, and considering all the numbers from 1 to n, the overall time complexity will be O of n into 2 to the power of d. And in terms of space complexity, it will be O of d, mainly coming from the recursion stack. And now let's jump into the code part. First, let's initialize the answer to store the punishment number. Now we will iterate through all numbers I from 1 to n, where n is inclusive, and compute the square of I. Now we will convert the square to the string and check if it can be partitioned into substrings summing up to I using can partition helper function, which we will write shortly. And if it can be partitioned, we will add the square to the answer. And once we are done with all the numbers, we will return our answer. Now let's write our can partition function, which will take in the square string and the target and make a call to another helper function. Let's call it helper, which will take in existing two parameters, square string and target, along with the starting index as 0 and initial current sum of 0. Now let's define our helper function. Now if the current sum exceeds the target, then we will return false immediately, to stop further exploration. Otherwise, we will write the base case. If we have come to the end of the string, then we cannot create more partitions. So we will check if now the current sum is equal to target. If it is, then we will return true, otherwise we will return false. But if we have not come to the end of the string, then we can create more partitions from next index up to the length of the string and create the partitions by extracting the substring from index to j and parse it as integer and call the helper function again to create more partitions but from index j and updated current sum by adding the current partitions value which we have just calculated. And if any of the recursive call returns true, then we will end the loop and return true. Otherwise, if we couldn't find any valid partition path, then we will return false. Now let's submit this code. Awesome. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.